Hello, Math 311. I'm going to make a quick video on teaching you how to compute determinants for a matrix. So first we're going to define it, what it is. We'll talk more about kind of what this represents later, but the main reason we need determinants is we want to get the eigenvalues of a matrix. And in order to compute the eigenvalues of a matrix, it's when the determinant is equal to 0. And so that will make more sense after the next video, but this is just going to be a quick video to show you how to compute them. If you've taken Calc 3 before, you've seen a little bit of how to compute these when we did cross products. We used the 3 by 3 determinant, but now I'm going to show you how to do it for any size matrix. I want to just record the definition of the determinant here. We won't actually ever, you don't need to be able to read this, but just so we have it in writing. What is the idea of a determinant? You have an n by n, so a square matrix, and we call the entries A, I sub j. Then what the determinant is, it's some form of multiplication where you take determinants of smaller matrices. And so what are these? A sub 1, 1, or capital A. So the matrix A sub ij is defined to be the matrix, the submatrix, so meaning a smaller matrix of A where you remove the ith row, jth column. So let me give you a quick example. So if, let's say our matrix is 1, 2, 3, 4, 5, 6, 7, 8, 9, then A sub 1, 2 is the matrix where I eliminate the first row. Oh, I didn't actually need to eliminate it. Where you eliminate the first row, second column, and so it's that. And so it's a 2 by 2 matrix. 4, 7, 6, 9. And so from there, the idea is that from a 3 by 3 matrix, by eliminating, what this is kind of saying is take the first position, A11, and then take the determinant of the matrix when you get rid of that first row and column. That will be that. And then you can keep doing this for the whole first row, and you have to add these negative ones. So the idea is that it alternates sign. And then what happens is you get determinants of smaller matrices, and we know how to take the determinant of a 2 by 2 matrix. The determinant of a 2 by 2 matrix, so the determinant of a 2 by 2 matrix, we have already defined earlier, but I don't remember if I recorded it, but I've defined it in Calc 3 class. But for those of you who have not seen it before, if you have a 2 by 2 matrix, that determinant will just be AD minus BC. This is going to be the determinant of a 2 by 2 matrix. So the idea is for bigger matrices, we're going to break them up until we get them into submatrices of 2 by 2 matrices, because then we get a number. And then what ends up happening is you get some number, and that determinant is some quantity that is associated to a matrix. In particular, we only really care when the determinant's non-zero or 0. But it also has some geometric properties, but we don't really have time to get into that. Our purpose is just computing them so we can figure out when they're 0. So let me do an example of computing the determinant of this guy. So how do we do it? So we'll do this is called cofactor expansion along the first row. So I take this first row and I say that the determinant of A is equal to the first entry, 1, times the determinant of the smaller submatrix when I get rid of that, and so the determinant of A 1, 1, and then you have to do minus for the next entry, 5, determinant of A 1, 2, and then plus 0 times the determinant of A 1, 3. And so this number right here, this determinant of A11 is when I eliminate that column, that row, and so it's that. And so generally we write this as just 1, and then we do long absolute value things to do just a determinant. And so I'd write 4, -1, -2, 0, and then minus 5 times, if I cancel out his column and his row, I get 2, 0, -1, 0. So 2, 0, -1, 0, and then this one will just be 0. And then to do this, it's 1, and then 4 times 0 minus -1 times -2, and then minus 5 times 2 times 0 minus -1 times 0 plus 0, And so this determinant will just end up being, this is positive 2, but then negative, so negative 2. And then this is 0 and 0, and so that goes away to 0. And so plus 0 plus 0. And so the answer is just negative 2. So the determinant of this matrix is negative 2. And so I haven't really quite told you what this number represents, but a kind of quick idea is that the magnitude of this determinant has something to do with kind of, if you view this as a linear transformation, like some sort of transformation from R3 to R3, because it's a 3x3 matrix, then this has something to do with kind of the area, or like how much it's scaling things by. The negative means that it's kind of inverting things, so it's not going in the positive direction, it's going in the negative direction. But I won't, for our purposes, we don't really care about what this number means. We need to be able to compute it, mostly because we want to know if it's 0 or not. When it's 0, something important happens that will be made more clear when we, again, we get to eigenvalues. But for now, we just need to practice computing them. Another way to do this, so this is what's called expanding along the first row. So I kind of take that first one, that's that value. I take that value that goes there, and I put a minus sign there. And then the third value goes there with a plus sign. So it goes plus, minus, plus. First value in the row, second value in the row, third value in the row, and then the determinant of the submatrices that come from blocking out their columns and their row. And so that's how you get there. And so in general, this can be done actually with any row and any column. And so that's called cofactor expansion. In order to do that, I have to define what's called the ij cofactor. So capital C sub ij will be defined to be -1 raised to the I plus j. So this determines whether it's plus or minus. And then it's the determinant of the matrix when you get rid of the ith row and the jth column, that submatrix. So this is what we're going to call C sub I sub j. And so the definition that we have for a determinant, this is called cofactor expansion in the first row, but we can do it in any row. And so it turns out that the determinant of A is actually, if you do cofactor expansion along the ith row, then it's a I1. So you take the first position in the ith row, and then the cofactor, which is just the -1 determinant of that submatrix. And then you add them all together, or you can do it down a column too, the jth column. And the same idea, you take all the elements in that column and you multiply by the submatrices with plus or minus 1, depending on whether or not kind of where it lands in the matrix. The easiest way to remember this negative plus or minus 1 is by this kind of checkerboard pattern. So any matrix, you always start with a plus, and then it always just alternates negative plus negative. And this is how you remember what the signs are. So for instance, if I go down the first column, it's going to go plus, minus, plus, so on and so forth. If I went down the second column, it'd go minus, plus, minus, plus. If I go down the second row, it's minus, plus, minus. And so I think the easiest thing to do is just do an example. And so let's do cofactor expansion along the third row. And the reason why we want to do third row is because there's zeros here. And when you have zeros in a cofactor expansion, it makes our life way easier. And so I like to remember what this is. So it's plus, minus, plus, minus, plus, plus, minus, minus, plus. And so along the third row, it's going to go plus, minus, plus. And so by definition, the determinant of this matrix, which we write as just absolute value bars, 2, 4, -1, 0, -2, 0, and cofactor expanding along the third row, I'll do 0 times the determinant of the submatrix, where I get rid of his row and his column, and so it's that guy. And so it's 5, 0, 4, -1. And then it's going to be minus -2, which is the second entry, right? So the second entry, blocking out his column and his row, get 1, 2, 0, -1. So I'm going to take the determinant of 1, 0, or sorry, 1, 2. 1, 2, 1, 2, 0, -1. And then finally plus 0, and then times. I don't really have to write this, but just so we practice, and it'll be 1, 2, 5, 4. But once you have a 0 there, we really don't have to even worry about that, because that whole thing is going to go to 0. And so this ends up just being 2 times the determinant of the second matrix, which is -1 minus 0. And so again, it's -2 which is what we got from before, I believe. Is that the same matrix? Yeah, it's the same matrix. And so we get the same determinant. That's good. And so the idea is that we use the fact that there's a couple zeros to make our lives a little bit easier. And so the computation we only have to really do 1, 2 by 2. And so picking what column or what row to expand along. And we could also do the same thing along the third column. And you go 0, -1, and then cancel out his. And so that's a simple way to do this. So let's do that again with an even more complicated matrix. And so we'll do, let's do cofactor expansion, and then what has the most zeros would be this first column. So cofactor expansion along first column. And then, so just a reminder, it's plus, minus, plus, minus, plus along that column. And so the determinant of A will equal 3 times, and then I don't even know if I want to write it, but it's going to be the determinant of A sub getting rid of the first position and our first row, first column, which we call A11. So it's that, getting rid of that. So it's that sub matrix. And then it's just going to be plus a bunch of zeros. Well, I guess technically it's -0 times, and then it really doesn't matter, but I guess it's determinant of A21 plus 0 times determinant of A31 plus, or that next one will be minus 0 times the determinant of just kind of cofactor expanding along this. So it's 0 times getting rid of his row, his column, his row, his column, and that's what these matrices are. And so it really doesn't matter what those things are because they're going to just be multiplied by 0. But just for completion, let's just write this first time. And so this just becomes 3, and then I can write the determinant of this thing right here. And so it's 2, 0, 0, 0, -5, 1, 2, 0, 7, 5, 4, -2, 3, 0, -1, 0. And then I'm going to do cofactor expansion again along this first column, remembering it's plus, minus, even though it wasn't, I don't think it would have been, actually, I guess it's plus, minus there too, but, and so this is going to equal 3 times 2, and then all the other ones are going to be 0, so it's really just this sub matrix now that I need to do. So 3 times 2 times the determinant of 1, 2, 0, 5, 4, -2, 0, -1, 0, and then plus a bunch of zeros, right? Because for the other, as I expand along this column, all the other terms are going to be 0. So it's really just that one times that determinant I have to look. But then this matrix is the one we already computed. That was this guy up here. And so that's just -2. And so the final answer is 3 times 2 times -2, which is -12. So the determinant of this whopping 5 by 5 matrix is just -12. Sweet. And so when you have zeros, we're going to leverage them. It makes our lives a lot easier. But what about, and what about if you had all zeros down here? Like, so it's a triangular matrix, meaning that above this diagonal, it's 0, or below that diagonal it's 0. Then when you cofactor expand, you just start multiplying all the diagonal entries, and so we actually get a theorem. If A is a triangular matrix, then the determinant is the product of the entries on the main diagonal. And so that is going to be really, really helpful. So for instance, if A is the following matrix, 3, 2, 5, 0, 0, 0, 4, 5, -3, 7, doesn't matter what the top entries are. The determinant of A is just the product 3 times 2 times 5. And so that's going to be what, 30? And so triangular matrices have really, really easy determinants. Whoops. You just take their product of the diagonal. And so let's talk about properties of determinants. So in general, this idea of cofactor expansion, where you kind of pick a column or a row to expand along, even for a 5 by 5 matrix, I mean, this can get disgusting really fast. And so it turns out that this is actually not the best way to compute matrices, or sorry, compute determinants. There's a better way, and it's using row, echelon, and row operations. And so, bring this down here. The idea is the following. If you have a square matrix, if you add a multiple of a row to another row to produce a new matrix, it has the same determinant. So that means the row operation of adding one row to another does not affect determinant. So we can do that row operation. However, if you replace two rows, or sorry, if you swap two rows, it makes the determinant negative. So you have to be careful about when you're swapping rows. And then if you multiply by a scalar, you have to multiply the whole determinant by that scalar. And so let me show you how we're going to use that with this property that a triangular matrix is just the product of the diagonals to actually simplify the calculations here. So if we want to take the determinant of A, then that's going to be equivalent to the determinant. If I pull out a 2 here, then I pull out a 2 on the outside. And so it's going to be 2 times the determinant of this guy. And so I can, pulling out a 2 in that first row, it would be 2 times the determinant of, so pulling out a 2 right here only affects the determinant by just kind of, you can actually just pull the number out for every time you pull out a row. And so that simplifies to -1 or 1, -4, 3, 4. And the reason I did that is because I want to do this row operation to eliminate that column. And so generally we want to do that to make our lives a little bit easier. 3, but if you can do the row operation of adding multiple row to another without doing that, then you don't have to, but making this a 1 will simplify our lives a lot easier. 0, 1, -2, 1, -4, 0, 6. And so then the idea is that the determinant of this matrix is the same as the determinant by adding multiples of this row to this row, this row, and this row. And so if I do those row operations, I'll do it very quickly. But and so if you want to slow down to do it yourself, I highly recommend that. But I'm going to add -3 of this to that to make that a 0. And so -3 times this gives me 12. 12 plus that gives me 3. -3 times that is -9 plus 5 is -4. And then -3 is -12 plus that is -2. Then I'll add 3 of row 1 to row 3, gives me a 0. 3 times this is -12. So I get a -12. 3 times this is 9. 9 plus that is 10. And then 3 plus that is 12 plus -2 is also 10. And then I will subtract row 1 from row 4. That gives me a 0, a 0, a -3, and then a 2. And so now I have a simpler, this determinant is much easier because I have a bunch of zeros in it. And I can actually make it even simpler and make it upper triangular by using this position to get rid of this. So add 4 of that row to get the other one. And so 1, -4, 3, 4, 0, 3, -4, -2. And then adding 4 of that to the other one gives me a 0. 4 times -4 is -16. Adding that gives me a -6. And then 4 times -2 is -8, -2. And then 0, 0, -3, 2. And so I'm almost done. I want to use this now to get rid of that, and then I will be triangular. And so I think I have to multiply this by what? -1/2 will make that 3, and then add it. And so this equals 2 times the matrix, not touching the top, or the second row, because I already did those, or the third row, 2, and then I get 0, 0. And so -1/2 gives me 3, so that's 0. -1/2 gives me -1 plus 2 is 1. And so this is the determinant, and this is upper triangular. And so now I can just multiply those. And so this equals 2 times 1 times 3 times -6 times 1. And so that's what? 6 times -6, so -36. So that's the determinant of this matrix. And we didn't have to do any cofactor expansion. We just did row operations. And so that actually will simplify things greatly. And so doing kind of product to make it to triangular, and then multiplying the product of the diagonals is kind of the simpler way to do it. The issue that's kind of a bummer is that when we get again to eigenvalues, we can't quite do this strategy. And so the cofactor expansion is still important because we're going to do it when we do eigenvalues, but that's the idea. And then you can kind of combine it all and do kind of these hybrid things where you maybe do a little bit of row operations, and then you can do cofactor expansion from there. It's kind of your choice, but I'll just end the video there, and then you can practice some computing these determinants. All right, thanks.